Okay, so let's not waste too much time. So it's my great pleasure to announce Matt Graydon, who's our guest today, or at least virtually, in these increasingly open times. That's good to see. So Matt did his PhD in Waterloo in Canada and did postdocs elsewhere, for example, in Hong Kong, to then return back to Waterloo. So he's back in his alma mater, working on mathematical structures in quantum information with a kind of emphasis on notions of, well, randomized benchmarking on the one hand, but also designs, geometric structure in quantum information. Also, the talk will be about designs in some way. So, so I leave it at that. And thank you for coming. And I don't want to waste any more time. So the stage is all yours. Thanks for being here.
Thank you very much for the introduction, Jens. It's a great pleasure to be here and share this work with your group. So the first thing I'd like to say is that this is joint work. So and the correct parts of the talk are also joint work with Joshua Scans-Norman and Joel Wallman. So Josh just finished his master's thesis, and I think if any of this talk interests you, I think that you will really find some other results in Josh's thesis particularly interesting. So I've posted a link down here, and I would like to advertise that. Right, so it's joint work with Josh and Joel. I'm going to demonstrate that the Clifford Group fails to enjoy the two design property in composite dimensions. Okay, so the Clifford Group on qubits, let's say, has powerful and existing applications in quantum information, both theoretical and experimental. So I am going to sort of cast a word of warning that these techniques will not generalize to systems with more than two perfectly distinguishable states. And that's sort of the plan for the talk. I should say there will be three sections. In the first section of the talk, I plan to give just a broad overview of the subject. In the second part of the talk, I'm going to collect some prerequisites from elementary representation theory of compact groups. And in the third part of the talk, I will present our theorems and proofs, and we'll do some other smaller proofs as we go along the way. So as I said, this is a theorem and proof style of talk, so please do feel free to interrupt at any stage. So we're all on the same page. The Clifford Group is the normalizer of the Val-Heisenberg group in dimension D modulo its center, namely U1. So I'm actually a little embarrassed. I hadn't realized Clifford died so young. So Clifford died when he was 33. Okay. I first started reading Clifford when I was interested in the quaternions. Okay. He is also famous for a premonition of relativity, right? So and also just, Clifford laid a lot of the groundwork for the low dimensional Lie groups and Lie algebras that would come in the centuries to follow, right? As a matter of notation, I will denote the Clifford group by CD. Okay, so it's the normalizer of the Val-Heisenberg group, WHD, in dimension D. And if you're not all too familiar with the Val-Heisenberg group, in dimension 2, so for qubits, this is the usual Pauli group. I've written down here at the bottom, so when the dimension is 2, the Val-Heisenberg group is the Pauli group with the usual X, Y, and Z qubit operators. I've written, you may wonder, so one needs an extra generator. So X, Z, and you still need an I around to generate the group. So that's why I wrote 3. I'm going to write the unitary group on a finite d-dimensional complex Hilbert space by U of HD. I'm going to write the projective unitary group as PU of HD. Okay. In case you're wondering where the name comes from, so in 1997 there was so this paper has been cited over 3,000 times. Okay. So in their revolutionary work on quantum error correction, Sloan, Shore, Calderbank, and Rains adopted the word Clifford group, the terminology Clifford group. And I've just pasted down here in the bottom their footnote. So they're actually citing a paper from 1960. It's 2 papers. It's like 1 and 2 in the journal back to back. So So it's on the Clifford collineation group by Bolt, Room, and Wall. And that's really where the name is coming from. However, a message perhaps to advisors not to leak really cool names to your students, because 4 years before that, so one of Room's doctoral students let Clifford Group slip in a paper. So a locus in 8, that 8 is antiquated notation for the complex projective space of dimension 8. Okay, so that's what that means. Right, so and one could probably keep going, but this is sort of how the etymology tracks. I'm going to be talking about the Clifford Group, and I'm going to be talking about unitary 2 designs. Okay. So one might be more familiar with the traditional definition of unitary 2 design in terms of a finite set of unitaries. So this is actually not the most, but here's a general definition. Here's a general definition of a unitary 2 design. What do I mean? I just want a measurable family of unitary operators indexed, but I want it to be an indexed family. And so I will say that it is indexed by some set G of unitary operators producing the second Haar moment and consequently the first. So if this bold X, so this is in the bounded linear operators on the tensor product Hilbert space. An example would be a bipartite state, right? But we're not just necessarily talking about the unitaries positive semi-definite linear operators. We're talking about the bounded linear operators. So this is what it means for an indexed family of unitaries to be a unitary 2 design. If we twirl over the whole family, that's the same as twirling over the whole unitary group. That's a definition of a unitary 2 design. They exist, and there are some deep connections to representation theory. So this G is not chosen by accident. This G is not chosen by accident. This G is often going to be a compact group, right? So I've put 2 papers here. The first on the right, Gross, Audner, and Eisert, is the seminal paper on group unitary 2 design. So what's a group unitary 2 design? It's a unitary 2 design that forms a group, a subgroup of the unitary group. That's what I mean by a group unitary 2 design. And in this paper, connections to representation theory are put on full display. So it's a great paper. And I'm also pointing to this paper from 1984. So you might say that seems a little out of place, the year. One can consider a general notion of so if I have some sort of measurable set and I want to reproduce the average. So here's the general idea. Imagine I've got just some general measurable set, and I'd like to reproduce some moments. I'd like to choose some points in a symmetric way such that when I take the average, it's the same as going over the whole space. Okay, so these have been around for a really long time. In fact, Cayley called them tactics, and it was Fisher in 1935 who changed the name to designs. So these have been around for a very long time. And in 1984, this paper of Seymour and Zyskowski, it's shown that they always exist. In every dimension, they exist.
And by the way, I mean, these are like spherical designs. So they exist both for complex and for real settings, right? The spherical designs in D dimensions.
Yes, exactly. And it's not just states, and it's not just operators. It's a general notion, right? So it's even more general than that in this paper. We have a measurable space. Yeah.
Okay.
But it's, well, here's an expert level response. Well, an expert level question, and I don't mean the response. So you know that you can't have ones of minimum cardinality in all dimensions when the underlying field is real. So for the experts, I'll say that real seek POVMs don't always exist, but that's the minimum cardinality. They do always exist.
Mm-hmm.
Okay.
Thanks.
Thank you. Tons of applications. So the Clifford group is fundamental, and so are 2 designs, right? I mean, they're absolutely fundamental in quantum information processing right now. I'll mention 3 applications. Okay, the first one is quantum process tomography. The references down here are respective, by the way. So in this paper from 2008, Scott shows that unitary 2 designs can be used to define optimal measurements for quantum process tomography. They also have cryptographic applications, and perhaps most pertinently for maybe even myself and some of the audience, randomized benchmarking. Okay, so I would say not the in capital THE, but you know, a prototypical example of how to do benchmarking is twirl over the Clifford group, and then you get a depolarizing channel with the same fidelity as the original channel. So that's how it's done. And right, but there's a problem. Okay, so yeah, I'm going to repeat the definition of the Clifford group here, because there's a generalization into the context of multiple quantum systems. So the multipartite Clifford group, I'm going to denote this by C, a bold D. So that's the normalizer of tensor products of local Val-Heisenberg groups, again, modulo at the center. So it's a very simple concept. It's a multi-set because the dimensions could be the same. And this bold D is nothing other than the vector of the local dimensions of the Val groups. Okay, so the multipartite Clifford group is the normalizer of tensor products of local Val-Heisenberg groups. I suppose the Clifford group is the special case of the multipartite Clifford group, namely wherein the cardinality of that D is 1. Okay, so that's the multipartite Clifford group, and there are some things known. So first of all, I will tell you that if each dimension is the same prime, then the multipartite group is a 2 design. Moreover, if that prime is 2, so for qubits, the multipartite Clifford group is actually a 3 design. And I've referenced Wenjun's paper here from 2017, where he proves that when that prime is 2, the multipartite Clifford group is a 3 design. I'll reference a paper later that shows the Clifford group to fail gracefully as a 4 design on qubits. Okay, so when the local Val groups are of a constant prime dimension, the Clifford group is a 2 design. So one can ask, does this property generalize? Okay. So, no. Those are the only cases. Right. So I'm going to spell it out explicitly. So if I've got a multi-set of naturals, the local dimensions of the Val-Heisenberg groups, then the multipartite Clifford group, first of all, it's not a unitary 2 design if any of those dimensions are different. If I have, so dare I say, even in cases readily amenable to applications, like say NISQ era cases where I've got even a couple qubits and a qubit, right? So I've got a couple qubits, I have a qubit. No, can't do it. Those are prime numbers, but they're different dimensions. And then moreover, nor is the multipartite Clifford group a unitary 2 design if that dimension is a constant composite number, so not a prime number. Okay, so that's the main result. The title of the next slide is Scientific Obligations, and that's exactly how I see it. So in 2020 of last year, in the New Journal of Physics, there was a paper published claiming the opposite, claiming that the Clifford group always was a 2 design. And then a little later, this actually appeared on the archive after this one appeared on the archive. So there are 2 papers claiming the opposite. I don't want to focus on these at all. I simply feel obliged to point out that they exist. And if you'd like to ask me later why the proofs fail, I'd be glad to go through that. But I would just like to actually point out that these papers exist. And I would also like to point out something to you that was pointed out to me by Marcus Heinrich. So in 2005, an author by the name of Benai did some heavy work on group unitary designs. And there's actually a 95-page pure math paper where, together with the classification of finite simple groups, one could see that the Clifford group is not a design. Okay, so it's not obvious. It's far from obvious. But my co-authors and I were very excited to learn about Vinay's work. So this is to some extent folklore knowledge. This is to some extent folklore knowledge. I guess I will just say that it is not folklore knowledge for everyone. So that's all I have to say about that. And the rest of the talk will just be going through the proofs of our theorems. Okay, preliminaries. So we're going to be talking
about. Before you still continue, maybe a question that I'm sure that I got the theorem right. So you say that it's also not giving rise to a 2 design if the dimensions are prime, but not the same.
Correct.
Oh, okay, interesting.
And you'll see what, I hope you'll see what, yeah, once you'll see. It's actually very simple. It's very simple. We just, let's all take on board some group theory for about 10 minutes and then we can see. Okay. So we're going to be talking about compact groups. So I'd like to just spell out that a topological group. So a topological group is first of all a group, right? It's a group, it's a set, it's equipped with, it has an operation that's associative, there's an identity, there are inverses. There's a topology on G such that the group operation and the operation sending little g to G inverse is continuous. So the group operation has to be a continuous function, and so does the operation that sends the group elements to their inverse in the group. So that's a topological group. We're going to be considering compact groups. So in finite dimensional metric spaces, one knows via the Hahn-Borel theorem that it suffices to show that a group is closed and bounded in order for it to be compact. Okay, so those are the types of topological groups that we're going to be considering. The running example is a finite group, but also any matrix Lie group like the unitary group. So it's like the unitary. So it's easy to see that the unitary group is compact via the Hahn-Borel theorem. First of all, it's closed because choose an operator norm, and then because of the unit modulus eigenvalues, it's contained in the unit ball, right? And then to see that it's closed, it's actually the preimage of a singleton under a continuous function. So if you consider the continuous function, so let's say x goes to x dagger, then the unitary group is the preimage of the singleton, the identity, and so closed, and it's bounded too. So by the Hahn-Borel theorem, it's compact. Okay, so those are the types of arguments and groups that we're going to be thinking about. Okay, there's the notion of a normal subgroup of G. So if I have a subgroup N of G, it's normal when that subgroup is invariant under conjugation under any element of the big group G. And there's a special symbol for this. One writes N is a normal subgroup of G. Okay, so here's an example, the center. The center of any group, okay, so the center of any group is just the set of elements that commute with all the rest, okay? So you can show that that's a normal subgroup. And because it's a normal subgroup, we can take the quotient of G modulo its center. And we're going to be talking about the projective unitary group. So I just want to spell out explicitly what I mean by this, right? Okay, so when I take G mod its center, I'm looking at all of the cosets at little g, okay, with the group operation defined like this. And the reason why it works like that is because the center is a normal subgroup. So the quotient of G modulo its center, it's all of the cosets extended by the center, okay? And the group operation works as you would expect. We're going to be talking about the unitary group, and for a while I'm going to run in infinite dimensions. So for right now, I'll just let U of H be the unitary group. So by unitary automorphism here, I'm in the context of vector spaces. So I mean a complex linear bijection that's unitary with respect to the underlying inner product. Okay, so the unitary group. Right, and then the projective unitary group. So the projective unitary group on H is U of H modulo its center, and there's an implicit isomorphism here. So I mean the center of the unitary group is just the scalar matrices, so scalars from U1. So I'm going to elide that isomorphism, and I'll just write the projective unitary group as U of H mod U1, which is the standard thing to do. Representations, the unit representations. So now we're going to talk about representations of compact groups. A unitary representation of a compact group G on a separable complex Hilbert space H is a group homomorphism. And by a group homomorphism, here I mean two things. I mean that it's a continuous function. And I mean that, so for all little g and little h in the group, pi of g times pi of h is pi of gh. That's what I mean by a group homomorphism. So that's a unitary representation. Let's talk about the irreps and such. Okay, so a G invariant subspace of the representation space is a subspace. So it's closed under the action of the group, right? So if I take any omega in the subspace and I look at the action of the group, I stay within the subspace. So that's the G invariant subspace. There are at least two ways you could define that. So a subrepresentation of pi on W is, so we're just regarding the image of pi of G as its formal restriction inside the unitary group on W for all G and G, okay? So if I have a representation with the G invariant subspace beneath it, we can consider a sub-representation thereupon just via the formal restriction of the image to the unitary group on that invariant subspace. Now, a definition and a big theorem. So the first one is a definition. So pi is irreducible when its only G invariant subspaces are trivial. So that's the notion of an irreducible representation. So pi splits into a direct sum of finite dimensional irreducible unitary subrepresentations. This is one consequence of the Peter-Weyl theorem, right? So maybe that's the first big theorem in like a last year undergrad course or first year grad course on group theory, the Peter-Weyl theorem. And so if I have an arbitrary unitary representation of a compact group G, it splits into a direct sum of finite dimensional irreps, right? That's how it works. Representations are determined up to isomorphism by their characters. So the character chi pi of a unitary representation pi is this functional. So it's a map from group to the complex numbers. You just take the trace of its image. Okay, so that's the character. And one can define an inner product via Haar integrals. So the inner product between the characters of two potentially different representations is this Haar integral. So here mu is the normalized Haar measure on the compact group G, and the overline is complex conjugation. It's a difficult theorem that every compact group admits a Haar measure. Okay. But they do. And one of the, so if you're not all that familiar with what the Haar properties are, so it's a, let me just be crude. So it's a measure. It's additive on disjoint unions. It's one on the entire group. That's the, okay. It's a normalized measure. Hence the. And some of the key Haar properties that we're going to use are, so not only is this measure invariant under left and right translations by elements of the group, it's actually invariant under left and right translations by any subset of the group. Okay, so that's the Haar measure, and this is a really well-behaved space. So there's the norm, right? So I should say for the experts that so for compact groups, the space of complex valued class functions on G is dense in the square integral functions. Okay, so that's how it works. And now we can do a really cool trick. So if I've got an arbitrary unitary representation, I can determine the multiplicity of the irreps just by taking inner products of characters. So the multiplicity m var phi of an irreducible unitary subrepresentation var phi in pi is just this inner product of characters. I said that characters determine representations up to isomorphism. It's a graceful failure of isomorphism. So on the one hand, we have the representation ring, right? So the representation ring is the free abelian group based on the isomorphism classes of mutually inequivalent irreducible representations of the group, all of the mutually inequivalent irreducible representations. So it's a ring with respect to a multiplication that works like how much multiplicity of this is in this. It's the details I will skip for today. The plus is the direct sum. So, but the point is that it's a ring over the natural numbers. Okay. Whereas on the other side, so for the complex valued class functions and the square integral functions, those are Hilbert spaces over the complex field. So while there is a one-to-one correspondence between the bases, orthonormal bases for the representation ring and the class function, there is graceful failure of isomorphism between the spaces because they're not over the same ground field. So that's why it's a graceful failure of isomorphism. Okay. One can loosen the notion of a projective rep and just consider representations that work up to U1 scalars. So formally a projective unitary representation of a compact group G in a separable complex Hilbert space. It's once again a group homomorphism. So now it's a group homomorphism into the projective unitary group. Now remember, these are the cosets. These are the cosets at the center that we did at the start. So this pi of G U1, so it's a set, and it's pi of G times every scalar in U1. So that's how a projective rep works. Okay. So notice that from any projective rep, I can construct a proper unitary rep via its conjugate tensor square. So at this stage, this is a symbol. Okay, this is a symbol. So I'm going to construct a representation from G to the unitary group on the tensor product Hilbert space that takes little g to pi of G tensor pi of G complex conjugate. And that pi is this pi here, right here. So you see why it works. So let's say I have pi of little g O times pi of little g complex conjugate times pi of little h O times pi of little h complex conjugate. So of pi of G pi of h times a scalar. And then on the other side, the tensor factor of pi of G times pi of h times the inverse of that complex scalar. So it goes, so this is a rep on the nose, as I'm sure you can see. The reason why it works is because there's an alternative definition of projective unitary representations in terms of so-called Schur multipliers or two co-cycles. So there are some details regarding associativity about how this map alpha has to behave, but the whole point is that, yeah, a projective rep acts like a usual rep up to U1 scalars, and that's why the conjugate tensor square is a proper representation, proper unitary representation. The conjugate tensor square is equivalent to the adjoint action, so inherited from the special linear group. So let me say that the induced adjoint action is another unitary representation of G. So it's a unitary representation. So unitary operators on bounded linear operators on the original Hilbert space. So there's this tower. And so little g gets mapped to add pi of G, and the add pi of G, the action for all little g is conjugation by add pi of G. So I've stated that the conjugate tensor square is equivalent to the induced adjoint action. It's going to be important for our proof, so I'd just like to prove it. I'll just show you that the characters are the same. So let H be a finite dimensional complex Hilbert space. Then these two traces are the same. Okay, so the trace of U tensor U bar is the same as the trace of add U. And this is really simple, so I just want to get us warmed up. So let D be the dimension of the underlying Hilbert space. Set an orthonormal basis for it. Okay, let's make a basis for the bounded linear operators thereupon, the usual 0-1 matrices. Okay. This is the definition of the trace. So I'm going to equip the bounded linear operators with the Hilbert-Schmidt inner product, and this is the trace. So it's the sum of the inner products with the basis vectors and the action of the map on the basis vector and the in the ket, right? So don't forget that add U goes like U dagger. So that's what's happening here. Okay. So now I will just sub in the definition of the Hilbert-Schmidt inner product. Okay. Now I will just sub in what the ERS are. Okay. Oh, I like this. I have R's on one side and S's two on the other. I can take traces now. Very good. Okay. And then the last two trivial steps. So the trace of the tensor product is the product of the traces, and the trace is invariant under the matrix transpose. So there you go. And the characters determine the representations. So the conjugate tensor square is equivalent to the induced adjoint action. I would actually like to come back now to one of the papers that I mentioned earlier from Gross, Ottenaer, and Isert. So there's a way to connect this stuff to algebra. And I should say that in this paper, the result is stated within the context of finite sets. But for this particular proof, the proof of the authors of this paper runs perfectly smoothly in the continuous case. It runs perfectly smoothly in the continuous case. So,
and with continuous case, you mean continuous measures instead of finite sets?
Yes, exactly. Yes, yes. So it works perfectly well. So now we can start doing linear algebra thanks to this lemma. Okay, so let mu be a normalized measure. So I've just got to normalize the measure on some indexed family of unitaries. Then that's a design if and only if this double Haar integral equals 2. Okay, so look, I mean, it's a frame potential. We've got the absolute values of traces and daggers and the number 2. This is just beautiful. We can do a lot of wonderful things with this. So here's kind of how the logic is going to work. I'm going to build on this lemma. I'll construct a lemma 2, okay? And then that lemma 2 will be crucial for the sequel. So that's what's going to happen now. And before I do that, I just like to spell out explicitly what I mean by a projective group unitary 2 design. So we had the definition of a unitary 2 design that produces the second Haar average, second Haar moment. Then a group unitary 2 design was one of those that's a group. Okay, so a projective group unitary 2 design is a projective unitary representation of a suitable compact group such that its multiplicative extension is a design. Right. So because it's a projective rep, I mean, one has to get unitary operators somehow. So this is the extension by scalars, and that's a mouthful. So I will probably say group 2 design a lot. Okay, I'll say group 2 design. Why am I citing this paper? So this is the paper where, well, amongst many other things, it was shown that the Clifford group on qubits fails to be a 4 design. But so this is a wonderful paper. It goes into some beautiful details about connections between representation theory and projective unitary T design. So this, if you happen to be wondering what a T design is, it's like a 2 design except you twirl over T tensor copies. So that's what that is. So this is what I mean by a projective group unitary 2 design. Here's a little lemma. So let G be a compact group and let pi twiddle be a projective rep. So then the following statements are equivalent. Generates a design. The conjugate tensor square admits exactly 2 irreducible components. Not more, not less. 2. Okay. And 3, the norm of the character of the conjugate tensor square is the square root of 2. Okay. So I'm going to prove it right now, and I'm going to prove the equivalence of 2 and 3 using words. So 2 and 3 is just group theory. If you remember, the square of the norm of a character is the sum of the squares of the multiplicities of the irreducible components of the representation in question. So the square of the norm is the sum of the squares of the multiplicities. Okay, so when that number is 2, okay, then there have to be exactly 2 irreps, right? So it's actually a special property of the number 2. Okay, so that's why 2 and 3 are equivalent. It's just some standard group theory. I'd like to now just show you that 1 and 3 are equivalent. Okay, so I've shown that 2 and 3 are equivalent. I'll show you that 1 and 3 are equivalent, and this is how I'm going to do it. I'm going to show you that the norm of the character of the conjugate tensor square is the root of this quantity, the square root of this double integral. Okay, I'll show you that this is the square root of this double Haar integral, and therefore by lemma 1 we complete the proof of lemma 2. Good. Okay, so let pi twiddle be a projective unitary rep of compact group G. Then, as I said, the square of the norm of the character is that quantity. So let's do the proof. Okay. First step, I've just written out what that quantity is. I've written down that double Haar integral. Okay. Now, for the first equality, I've done 3 things. First of all, I've applied the group homomorphism property, and then I've applied the fact that we've got a unitary projective rep. So the dagger works like the inverse up to scalars. Okay. And then I have pulled via linearity of the trace, I've pulled out the Schur multiplier. Okay, so this 2 cocycle, I've pulled it out of the trace via linearity. Okay. Wait, so I've got a U1 scalar inside of an absolute value to the 4. Oh, that disappears. Okay, so all I've done here is I've pulled out the U1 scalar. I've pulled out this alpha, which is in U1, and I pulled it outside of the absolute value to the 4. Okay, that's all. I'm going to do this slowly. So let's use, I want to do this integral, right? I want to do this integral. So I'm going to use invariance of the Haar measure, okay? And I'll put a G inverse here. Now, 2 things next. Fubini's theorem and change of variables, okay? All right, so I change variables and use Fubini's theorem to split the integrals, okay? Well, the Haar measure is normalized, so we're just left with that one, okay? We're just left with that one. And the rest is just okay. There are many different ways that I could write this quantity, absolute value of the trace to the 4. Let me write it like this, okay? So first of all, so bar, okay, so there'll be 2 bars and there'll be 2 non-bars. So that's how we're building back up to the absolute value to the 4. But why have I written it like this? Well, I've written it like that because that is precisely the definition. Okay, and so that's the end of the proof.
So that's a more convenient way of writing the frame potential that you're going to use in the next slide, I suppose, right?
Well, I don't know if it's more convenient. I should say that the proof is very similar to the proof that happened in your paper. The only thing that really needed to change was dealing with these 2 cocycles, which disappear anyway.
Wonderful, thanks.
So it's a very simple proof. Thanks to your lemma. Okay, here we go. Let's see how much time. I think we might have started a little late. Okay.
So one small question. What you mentioned, you said that you only had to care for this 2 cocycle appearing, and I see why that's easy. Could you just repeat again why your way of generalizing the problem yields to exactly only going from a linear representation to projective representation? Like, why is it that only the projectiveness of the representation changes?
I think I'm going to reject the premise of the question. So it's not the only. So let me just keep going.
Okay, so it was only for this particular theorem where it was the only difference. Okay, then.
And actually, but I don't want to be too tongue in cheek. There's in the discussion, there's something that I'll come back to. Okay. Let's take, just for 5 minutes, a good hard look at the Valhalla-Heisenberg group, okay? So the Valhalla-Heisenberg group in dimension D, I'm going to be following the paper so on the very first slide, I had a reference to Marcus Appleby's heavily cited paper from 2005 with an absolutely beautiful exposition of many of these groups and some basically of the generalizations too. So I'm going to be following Appleby right now for this slide. Let HD be a finite d-dimensional complex Hilbert space. Okay, so we're dealing in finite dimensions. I'm going to really throw you off because before my basis was 1 through D and now it's 0 through D minus 1, but I throw myself off. So pick an orthonormal basis for HD. Okay, define the phase and shift operators like this. In dimension 2, S is the Pauli X, right? So this just cycles the basis vectors. Okay, so this is the clock. And in dimension 2, T is the Pauli Z. So this adds a phase, a root of unity. Here's our omega right here in case you're wondering what the omega. Okay. So those are the phase and shift operators respectively. Introduce Appleby's tau. So this phase convention is particularly beautiful because whether the dimension is even or odd, tau to the D squared equals 1. Okay. Here are the Valhalla-Heisenberg displacement operators. So I'm going to they're labeled by elements of the integers modulo D Cartesian product with itself. Okay, so the displacement operators are labeled by these vec p's, and I should say for later, those p's are not prime numbers. They're numbers in ZD, okay? So this is just a matter of history that it's a P. So it's a vec P. These are the displacement operators. And I'd like to show you how the group operation works. However, there's some funny business in even dimensions, okay? Which might lead you to believe the F stands for funny, but I can assure you it does not. So f of d equals d if d is odd, and f of d equals 2d if d is even, okay? So there's some funny business. I'm going to introduce a symplectic ZD bilinear form, and by symplectic form, I want to remind you that it's 0. So I want to remind you that that omega is 0 on PP, so it vanishes when the arguments are the same. It's alternating, so omega of PQ is minus omega of QP. And it's I forget it's called definite or something, but if one of them is 0, then it's 0 if and only if one of them is 0. Excuse me, if they're different and it's 0, then one of them has to be 0. Something like this. So this is some symplectic form. So here's how the group operations work. Okay, so it's like ZD squared projectively, but the phases are crucial. So if you multiply any of the displacement operators, you get another one up to a phase. And the dagger works as how you would like it. And those are the Bell-Heisenberg displacement operators. There are d squared of them, and they're literally independent. Okay, so they're like the Pallies, except they're not self-adjoint anymore. That's what you lose when you generalize above dimension 2. You lose self-adjointness. Okay? And I'll define the Bell-Heisenberg group as generated by the displacement operators. You can generate with any phases you'd like. That's not important here. So it'll have cardinality d cubed when d is odd, and 2d cubed if d is even. Now,
one small question again, if I may.
Yeah.
So these d's, as you said, form a representation of ZD squared.
No, I said that. I said that.
Projective. Yeah. So that was basically where my question is going. So is it known, or like with this phase factor in front, to which equivalence class of projective representation does it correspond to? Is that important, or because there should be d of them, right?
Okay, so I think I want to. This is now good. I want to digest your question. So you're asking whether or not the phase convention creates. So whether two different phase conventions will create two mutually inequivalent projective unitary representations of ZD squared. Is that what you're asking?
Yeah, because you could redefine T and S respectively with like a global phase factor, and then you obtain a different tau.
And the character will change. The character will change because of the phase. Yeah. That's actually totally beautiful. I just don't know if the answer. So I don't know if the answer to your question is D or 2D. Because there might be some funny business again in even dimensions.
Okay, so I know that there are like the second cohomology group of ZD squared is ZD. So there are D in equivalent projective representations for ZD squared.
Well, then
this is a fact. But so, actually, because in which equivalence class this projective representation is actually tells you how to find the irreducible subspace or the irreps.
Okay,
like how to diagonalize this. So
first of all, I'm gonna stop because I'm not talking about projective representations in this talk of the Bell-Heisenberg group. Okay, I'm not going to be dealing with I'm going to be dealing with a proper representation of the Bell-Heisenberg group. So I'm okay. I'm going to stop there and say that I'm really interested, and let's talk in 20 minutes.
All right. Yeah.
Okay.
Yeah.
Just in the interest of time. So the Bell-Heisenberg displacement operators can have different orders when the dimension is not prime. Okay. I'm going to show you an example first. Okay. Here's an example in dimension 4. I should remind you, the order of a matrix need not exist, but when it does, it is the least natural number, say R, such that when you raise the matrix to R, you get the identity. So the order of a matrix need not exist, but when it does, it's the smallest power that gets you the identity. Okay, it's the smallest power that gets you the identity. So I'm going to show you a lemma that there are at least three. Okay, there are at least three orders amongst the Valhalla displacement operators. There are actually more. I'll show you at the end. But I just need to know for the proof that there are three. Let's look at d equals 4. So consider the square of the shift operator. It looks exactly like this. Okay, so there's the shift operator in dimension 4. There's its square. Everyone recognizes that matrix. Depending on your tensor product convention, it could be the reverse, but so that's x into the identity, right? So that's an order 2 unitary. So the shift has order 4, this guy has order 2, and the identity has order 1. So there are at least 3 orders. Okay. In general, I now just generalize it. So in general, so in all dimensions, the order of the identity is unity. Our premise is that the dimension is not prime, and so we may choose P and Q and ZD squared as follows. Okay. The fundamental theorem of arithmetic says that we can write the dimension as we can write the dimension in a unique way as the product of prime powers. I'll split it. So if the dimension is a prime power, so if that little n equals 1, if the dimension is a prime power, so okay, if the dimension is a prime power, then I'll choose little a equal to that prime, and I'll choose b such that p1 does not divide b like before, and then dA0 has order d over p1. So before that was 4 over 2, which is 2, right? Well, this one has order d. Okay. And then if d is not a prime power, it's almost easier. Just choose two distinct primes, and the val operators. The val operators corresponding to those displacement operators have those respective orders. So there are at least 3. Okay, at least 3. Now we prove it. Okay. So let D be not prime. The Clifford group is not a unitary true design. We have all the pieces. Okay, let's fix a unitary representation of the Clifford group like this, okay? Well, we're going to recognize that. That's the adjoint action. That's the adjoint action. So let's consider the adjoint representation, right? Okay, that is equivalent to the action of the conjugate tensor square. We proved it. Okay, so we're considering the adjoint action, and we know that that representation is equivalent to the conjugate tensor square. Step 1. What does this mean? It means that the irreps of phi are in 1 and 1 corresponds with the irreps of the conjugate tensor square. Okay. Now, since D is not prime, I just showed you, then you can find at least 3 distinct orders amongst the Valhalla-Heisenberg group, not the projective Valhalla-Heisenberg group, the Valhalla-Heisenberg group. Recall the Clifford group by definition is such, so it's the normalizer of the Valhalla-Heisenberg group. However, if a certain displacement operator has order R, then so does UDP U dagger for any unitary, not just a Clifford unitary, for any unitary. There must therefore be at least 3 irreducible components of phi. Okay. It remains only recall lemma 2. Okay. So we showed that there were more than 2 irreps in the conjugate tensor square. I'll pause for questions.
Well, obvious corollary of your statement is that, I mean, the Clifford group on a system where like pairs of qubits are considered as a 4-dimensional system are also not unitary true designs.
That's correct.
Interesting. Yeah.
Okay. I'm glad. So I mean, it's the same proof. So for the multipartite Clifford group, it's the same proof, and now it's either even more orders, by the way. So I've taken the time to write it down, so I'll just spell it out. It's what I wrote before. So the proof is exactly the same. If I've got some collection of quantum systems, so I've got some collection of quantum systems that each have a local dimension. Okay. Then the Clifford group is not a 2 design unless those dimensions are the same number, and that's a prime number. Okay, so that's, and the way you prove it is exactly the same as before. Okay, and again, use the fact that since each of the local Valhalla-Heisenberg groups span their ambient space, their tensor product spans, because we're in a complex category. So yeah, that works. Questions and discussion. The first one. So the first, I think there was a question earlier on about generalizing and things like this. So I'd like to come to your point now. A natural question arising from our analysis is whether or not, so this business of the conjugate tensor square, is it all, you know, I mean, could we have used lemma 1 all along? No. So a natural question is whether or not the tensor square and the conjugate tensor square are always equivalent. And the answer is no. Okay, the answer is no. I'll show you a counter example. So I'm just going to be considering a unitary representation of symmetric group on 4 symbols into 2x2 unitaries, even just diagonal ones, right? Even just diagonal ones. You see what's going to happen. Okay, so consider this and look at its tensor square and look at its conjugate tensor square. Well, the tensor square is going to have 2 copies of this guy, but the conjugate tensor square is only going to have 1 copy. Furthermore, the conjugate tensor square is going to have 2 copies of the trivial representation, whereas the tensor square is only going to have 1 copy of the trivial representation. So no, these are distinct notions, and it takes a little bit of work to start thinking about designs in terms of the conjugate tensor square and the adjoint action. The real reason for this talk to consider the adjoint action is just because it's so perfectly set up to finish the proof of the main theorem. Like the whole point is that there are lots of different orders, and now that you've seen it, yeah, if I conjugate by a unitary, that preserves the order, right? So there's going to be lots of different irreps of the adjoint action, and consequently via lemma 2, the conjugate tensor square. Or proposition B. Sorry, it wasn't lemma 2, it was proposition B, in case anyone was wondering. Okay, I've been alluding to it all along. Okay, so this did not make the paper, okay, but it's on my desk. It actually is. And so this is a map of the Valhalla-Heisenberg group. Okay? So if someone comes up to me and says, Matthew, what's the order? You know, all day, I work from home, right? So all day long, my kids are coming up to me. Oh, what's the order of this vowel operator? I wish. In any case, right. So this is how it works. This is any Valhalla-Heisenberg group element looks like tau to the k. So Applebee's tau to the k dp, right? So tau to the k dp. So how do I figure out the order of that? Okay, let's hinge on the phase first. Let's say you've given me a phase factor of 1. Okay, so now I go to that dp. Well, are both entries 0? Oh, you've given me the identity. That has order 1. Okay, so now let's try another example. Let's pretend that the phase is still nice. So it still have 1. It's just the product of the shift and powers of the shift and phase. Let's suppose that those powers are both non-trivial. Then here are the possible orders. So if that vec p, so if its entries are such that p2 divides p1 divides d, there's the order. Or if p1 divides p2 divides d, there's the order. If none of those divisions can happen, then the order is d. Or let's try another example. Let's say, okay, the phase isn't 0. Now I have to split according to even and odd dimensions. So let's say the dimension is even. The phase is non-trivial and the dimension is even, and both of the entries are non-zero. Okay, well, here are the orders that can happen depending on cases of division. So it gets a little nasty, but these are all of them. And I guess I'll just point out, yeah, when D is a prime number, none of the divisions can happen. So that's why in prime dimensions it's still okay, right? But when D is not prime, there are many different orders happening. I said it didn't make the paper, and then I joked about the kids, but the serious reason it didn't make the paper is because your phase convention will disturb how you have to move these cases around. So this is with the Appleby phase convention. These are the orders of the Valhalla group elements with the Appleby phase convention. Okay. I'm glad to see we're on time, so that's great, and I really appreciate the questions as we went along. I do. They always exist, and the Clifford group isn't one of them in composite dimensions. And I think now I'd be just delighted to talk more and accept any questions that are lingering around. And thank you so much for being here on your Friday afternoon. So thanks a lot.
Wonderful. Thanks, clap, 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 for this wonderful talk. We had some questions, lots of questions along the way, but I'm sure there's more questions, or the stage is open. So let's clap.
One question. If I have like a prime dimension, or I have 2 qubits or something like this, where I have like this property, and I somehow hide my qubit in there. So does your result tell me that if I restrict like this Clifford group to this qubit that is hidden in there somewhere, that it's not a Clifford group on this restriction?
You say you have some qubits in a Q-trip, but you're hiding the Q-trip.
So I mean, let's say I have a Q pit with P prime, and then somewhere in there I hide a Q-trip.
So just the subspace of this composite group.
I see what you mean. So you're asking whether the restriction of the Clifford group on the big system to a subsystem of prime dimension would be a 2 design.
Or let's say, I mean, or let's see, even if it's non-prime, or if it's let's say like 4 non-prime. I think that's
no,
the most
no, it's not. It's not prime, no.
Because it can't be, right?
Yeah.
Yeah. Okay. Good.
I guess a simple conceptual question. So, as in the last slide, you emphasized that there do exist for any number n, there exists the 2 design over Hn, or over the unitary group, whatever. Not sure how to correctly say it. In the sense, what is your, like, you defined the 2 design some representation over some, not even a representation, just a map from some index set to unitaries. Like, what is your constraint on the index set that you call it? Like, if it could be anything, then obviously the trivial map from unitaries to unitaries with unitaries parameterizing unitaries is always a 2 design. So that's why, what is the restriction?
Yeah, so I think the reason I said it was not the most general definition is because I think that if you define it in the way Jens has done it more recently, in terms of just defining a design as a measure on the unitary group, that might be a slightly more general notion. So there's a now, I think I would say the ultra modern definition of a 2 design is just a measure reproducing the second Haar moment, whereas I want an indexed family. And I'm waiting for someone to prove me wrong that an indexed family is more restrictive than just an arbitrary measure on the unitary group. But I feel that it is.
Well, I mean, you could always kind of define the measure that is the spike measure on your index, on the map of your map from index group.
Yeah, but the other way around, are there cases covered by the measure definition that are not covered by my family definition?
I mean, I guess that's again a question of like, I mean, probably this can't exist, but like if you could have a measure which is non-uniform measure, like say maybe it's a smeared out version of a spiked measure around the Cliffords.
Yeah.
Then this, I'm not sure, but maybe if you have some Gaussian smear out around the Cliffords, then maybe this is still a 2 design for prime numbers. Maybe not, I don't know.
Oh, well, so now you're asking 2 questions, or at least I'm hearing 2 questions. The first question I'm hearing was to do with the general notion of the design. The second question I'm hearing is about a fix. So if you somehow can, so I mean, if the Clifford group isn't a design, I'm hearing the question, well, what if we smear what if we smear the distribution around where the Cliffords are? Could that somehow reduce the number of irreducible components in the adjoint representation? Is that the suggestion?
Maybe, I don't know. I think my motivation was more like you were conjecturing that, like, there's the modern notion of design, which is measure theoretic, and you said, like, you conjectured that you think that any 2D design in this notion can be also explained in the index set framework. But as soon as you have a measure that is non-zero on every, like, that is a measure that is non-zero everywhere, like a smeared out measure, like it's maybe just exponentially small, but it is everywhere, then this, I mean, I'm not sure how you would phrase this as an index set thing.
That's okay. That's why I said, okay, it's okay. That's okay. That's fine. I conjectured that my definition was the subset of the general definition. I did not conjecture the other way around.
Ah, okay. I mean, then your conjecture, I guess, is easy to be seen true.
That's why I said it, because I didn't want to be wrong.
Another question, like when we're talking about those measures, I mean, do you think there exists like a measure on the Clifford operators, which is not uniform, such that you have like a two-design property?
No, because it's still, I don't care if there's, I don't care if you weight them. It's still, they're still gonna have to have different invariant subspaces according to how they act on the val operators. So no, I don't think, even if you weight them, like weight them either with constants or weight them like inside of an integral, like in a fancy way, I still don't think so. No, not if you just weight them. No.
Mm-hmm. Of the obvious question, which is like, when the Clifford group is no 2 design, as you say, and beautifully say. So like, what does one need to add to get a group unitary design, which is not the full unitary group? I mean, my example from earlier, like this, like treating pairs of qubits as a subsystem is like maybe instructive, because there's 2 Clifford groups, like the coarse-grained Clifford group and the actual Clifford group, and like one is a subgroup of the other. So, I mean, is there a way of finding out what you need to add to get a group unitary design as a supergroup of the Clifford group?
So I can tell you how many irreps that you have to get rid of.
Okay.
That's for sure. From this table. So I mean, I can tell me how many irreps you have to get rid of, okay, but I do not know how to extend the Clifford group to make a 2 design on prime dimensions. That's a really interesting open question. Josh and I were thinking about that just the other day, actually. So yeah, it's totally interesting open question, but we have to get rid of quite a few irreps.
I think it's a natural question, right? I mean, it slams in your face. I mean, after all, of course, you want to.
Okay, thank you so much, because there's some other natural. So here's something I'll say. There's a fix. Okay, so there's a fix, but it's forthcoming. So there's a next best thing that's even better, actually, but I can't say what it is.
Okay.
I know that's not helpful. Okay, so let me give you some other answers. If you look back to it, okay, Clifford group's not one of them, but I want to use a design. Well, they exist. Okay, they exist. So if you've got a couple qubits and a qubit, then fine, yeah, go find a nice design. You can, the way you could do it is, I mean, I think in that original paper from 2000, it was put in the archive in 2006. It was published in 2007 by Isert, Gross, and Odner. So in that paper, they've actually gone into the gap system and harvested character tables. So I mean, there are some there are some examples of designs, right? Like there are some nice examples, right?
That's right. I mean, for most dimensions, we could find a group design in like totally obscure finite groups. That's right.
So that's all I'm going to say. I'm sorry to be evasive, but yeah. So soon on the archive you will see that there's a fix.
Mm-hmm.
Sorry, can I just point out the Clifford group is maximal. That means if you add anything to the Clifford group, it becomes the unitary group. It generates the full unitary group. So there cannot be a super group of the Clifford group.
So.
Well, that depends. Is that so? I mean,
what about your?
Oh well, I mean,
no.
What about my coarse graining example? I take the Clifford group of pairs of qubits, and then I look at the Clifford groups of the fine grained Clifford group. One is a subgroup of the other, and they are both.
That's a subgroup.
Yeah.
You were talking about the supergroup, like something that contains the Clifford group, right?
Yes, and you claimed it was maximal.
Yeah, but look, I go from the coarse grain, like the coarse grain Clifford group, like treating pairs of qubits. That's not a Clifford. That's not a 2 design because it's not prime. Okay, but this I can extend to the Clifford group over qubits or not?
No, but I think but I mean it's a really cool Jonas. I think that your point is like important to sort out. So here's what I think Jonas is saying. He's saying that like no, I'll apologize. Here's what I am hearing.
I don't know. I see the point. Okay, but it's both right. Yeah, I see the point. Sorry.
Here's what I'm hearing.
Okay, I see. Yeah.
So the Clifford group was so it's maximal in the sense that if you add another element, you have to get the full unitary group.
Exactly, but adding the element, that's the tricky.
It's probably only maximal in prime power dimensions.
That's the point. That's the point. Exactly. Yeah.
Oh, okay.
So you're kind of both right in the sense.
So sorry.
Thank you. Okay, that's really cool. Does that mean that it's singled out by our Cartan involution on the ambient Lie algebra?
I didn't get this, but
so the maximal compact subgroups of the unitary group are in one-to-one correspondence with Cartan involutions on its Lie algebra.
It's a discrete subgroup, so probably this holds for connected subgroups only.
It doesn't have to be discrete. Use all the scalars.
No, I didn't. I joined late. But the Clifford group, I mean, if you cancel out the phases, it's a discrete group, right?
Of course, but I'm saying if the Clifford group. Oh, I'm very sorry, Jonas. Are you saying that it's a maximal compact subgroup of the projective unitary group or of the unitary group?
Of the unitary group, even.
Okay, so in that case, there must be an involution.
Let's stick to the special unitary group. That's easier.
Then there's still, So what's the Cartan involution? That's an interesting question. So if it is maximal and compact, then there's a Cartan involution on the Lie algebra that singles it out.
I don't know.
I just never thought about it being maximal, but that's super interesting.
Yeah, but I think this is basically this is just the statement that Clifford plus anything that's not in the Clifford group is universal.
Yeah, exactly.
It's really old.
Yeah.
I can interpret that way. Yeah.
I think, but
Oh, then there's an awesome connection to the Lie theory that I hadn't even thought about before. Thank you so much. Thank you.
Like recently in the context of our learnability of output distributions of circuits, the question came up whether match gates or random match gates would be unitary designs, 2 designs, which they're not. I mean, it's quite easy to see. I mean, they in the sense they generate the spin representation of SO2n, and then one can look at representation theory thereof. Is there? I mean, is your approach giving any insight here, on the frame potential of the match gates? Is there something, a simpler argument through your lines of thought that match gates don't give rise to 2 designs?
Okay, so you said SO, right?
Yeah, I mean they're not a 2 design. I mean the particle numbers, they don't talk. I mean it's just the direct sum of different particle numbers that are.
Oh, no, I understand. I'm just trying to, so we're talking about the real case then. It's-
Yeah, that's right.
So-
That's right. That's
So,
right.
so I think, so an SO2N design would have the same number of ERAPs as the tensor square of SO2N, right? So that's what
right.
one means. And I think the thing with the matchgate group is that it has more. It has more than that has more than 3. So there have to be 3, not 2, but there must be 3, right? And how that works on the state level, how that works on the bipartite state level is that the symmetric subspace picks up an additional one-dimensional ERAP, right?
Yeah.
So, and by the way, for SP, for the quaternions, it picks up an extra, it's 3 again, but it picks up an extra ERAP in the anti-symmetric subspace. Yeah, but so if you wanted to show that something wasn't a design, yeah, can't you just follow the same technique and show that there are more than the number of ERAPs are allowed by this generalized Cheval?
I would think so. Yeah, I think so. Cool. Thanks. Wonderful. Are there more questions?
I'll ask a question that might be a bit basic. So if these Cliffords don't always form 2 designs, does it make sense to ask how close they are to a 2 design, like some approximate notion?
It totally makes sense. Yeah, it totally makes sense. So there are a couple answers to that question. The first one is that, like, okay, you could count the number of ERAPs. So I think there are 7 or 8. Okay, so a 2 design has to have 2, and it's got quite a few more. So if you're doing benchmarking on these guys, I'm gonna have like 7 or 8 different parameters that I need to get estimates for. Okay.
Okay. Mm-hmm.
And another way to see it is that oh, right, here's another answer to your question. So it probably is not the answer you wanted. So they're always a 1 design. They're always a 1
Right.
design. The Clifford group is always a 1 design.
Okay.
And the reason that that's true is because the Clifford group contains the Valhalla group as the normal subgroup, and the Valhalla group acts irreducibly on its underlying complex Hilbert space, and therefore via a paper from AJ Scott and Aidan Roy in 2009, the Clifford group is a 1 design. So it's always a 1 design. And in terms of norms and stuff, for terms of approximate, I have not done the norm calculation. So I'd actually be interested to see. I'd be interested to see what a calculation involving the diamond norm on the measure or something like that. Yeah.
Something like that. Yeah.
Yeah.
Cool. Okay.
Question. Yeah. Wonderful. That's great.
Yeah, because I mean, it's some epsilon away, and then whatever that epsilon is, it could be useful somehow still, maybe.
I think it's a big epsilon because of the number of ERAPs. I think it's a big epsilon.
Okay.
Yeah.
I mean, I have no idea, so yeah.
Although epsilon just has to be bigger than 0.
Right.
Wonderful. Yeah, thanks so much. Yeah.
Also have another question regarding, like, back to the ZV squared thingy
Okay.
from before. Like, just because I think I've wrapped my head around about what you do in this subpart. Namely, did I understand correctly that you sort of show that the Heisenberg-Weil group, or sort of its representation is isomorphic to a projective representation of ZV squared, right? Because as you said, you are just interested in the proper linear representation of the Heisenberg-Weil group, and you sort of map it to a ZD squared label, but then observe it's a projective representation.
I did do that.
Okay, so and so in the end, you diagonalize these the Heisenberg-Weil group, right?
No,
you don't. Okay, but you find the ERAPs thereof, so you.
No, I found the ERAPs of the Clifford group.
Okay, so the Heisenberg-Weil not U1, that was.
Well, the Heisenberg-Weil group is the ERAPs are trivial. It always actually reduces in every dimension. It's a unitary operator basis in every dimension.
Yeah, okay.
It's a unitary operator basis in every dimension. But I thought about your question, and I think I see what you're saying, because so I didn't know this. So that Appleby tau, are you saying that Appleby tau is one of D canonical choices for the phase?
Well, I mean, depends what you mean by canonical. interestingly, I had this discussion about the canonical choice just this day, like just today. But
Nice.
besides that, so I mean, yeah, depends what your canonical choice is. What I was actually thinking about was if you have some guarantee that this tau is in the trivial equivalence class of projective representation, then it's actually quite easy to diagonalize the corresponding, like to find all the irreps. Because then, since this phase factor is trivial, you can write it as a co-boundary of something, and then this something just modifies your regular Fourier transform that you use for diagonalizing. But if your tau is in a non-trivial equivalence class, then it's not so easy anymore. That's why I was asking. Because in one case, it's quite easy, in another case, it's difficult. And I suspect that since your diagram is quite branched out, it depends on the dimensionality and so on, if this phase factor corresponds to a trivial equivalence class or a non-trivial one. But
Do you know if alpha b tau corresponds to trivial?
Could you go back to the slide? So it's
I actually
basically
don't think it does, but
no. I mean it is.
Here's the group.
Okay, so it's tau is sort of the square root of the dth root,
Yes.
right?
Yes.
Okay.
Yeah.
And then the symplectic. I'm not sure, but it's not f of d. F of d is 2d. Well, I can't see it directly, but it shouldn't be so difficult actually to see it. Wait, minus. I'm not sure about the factor of 2, but it could be that if you would have 2 pi over d times this symplectic inner product, then it would be a trivial one, like a trivial projective representation. But
so that's the standard one. So that's the omega at the top.
yeah. So the standard. So what I would consider a canonical representative of the non-trivial, sort of the generator of the non-trivial projective representations would be exactly this tau with P1, Q2, just one of these factors. And now you have in your symplectic inner product, it's sort of the sum of two such terms where one index is interchanged, and the interchanged index is actually is in the same equivalence class as the. So you basically multiply a sort of the generator of the non-trivial ones with the inverse of the generator, just in a different gauge. So you would be in a trivial one. But I don't know about the factor 2. This might kill everything. So
see, the F is for a reason. Okay.
I have a quick question.
Yeah.
Early on, I think in the introduction or something, you showed 2 papers, like including a new general physics paper. That did they arrive at contradictory results to you, or?
Yes.
So is it easy to explain why?
Yes. Okay. So in the first paper, so they're relying on a 2017 paper by Zach Webb. So Zach Webb and Huangjun Zhu in 2017 both put a paper on the archive showing that the Clifford group was a 3 design for qubits. Okay. And it is the paper by Huangjun that I referenced in this talk. Okay. So that's the first thing I'll say. It is the paper by Huangjun that I referenced in this talk. And if you look, so this is, I pulled these 2 sentences from this paper. You'll see that they say it forms a unitary 2 design based on Webb's analysis. Okay. So that's all I'm going to say about that. And the second one, the proof is, yeah, just no. They try and generalize the existing case, but make some mistakes. But the first one. So by the way, I actually I've got a friend on here. Like I've got a friend on one of these lists. Like I I don't want to say too much, but yeah, it's not Pally mixing. It's not. It's not.
Are the papers still out actually? Are they still on the still online, or are they withdrawn, or what's the?
I have not noticed any action.
Okay, interesting.
The thing is that okay, here's the thing.
things?
Here's the thing. Our proof. Okay, if you for this group, I'm able to say it. So if you're able to take on some group theory, the proof's really easy because the order is preserved, and they just need to show that there are different orders. Okay, so our proof is really simple. Like it's not a complicated theorem, right? It's not a complicated theorem. That's something else I'll say about this slide. Okay. Sorry, Jens.
Yeah, good question. So we had lots of questions. That's a good discussion. Thanks for this. That's really great. Is there a further question? So
I have a very basic question.
Yeah.
You said it's clear that in every dimension there exist designs, but is it clear that you have a finite set that is a design?
No, I'm checking my repository. I'm trying to see if there's... Yeah, I want to say yes. I want to say yes so badly, but I'm going to check off here. I want to get you the answer. Oh, can you see it? Oh, you can see it. Okay, well, look what I'm checking, right? So this paper is awesome. Look, main theorem. Yep, finite. Yep, finite. Finite. This is the.
Okay, cool.
So X.
Seymour.
Yeah.
Yeah.
Wonderful. Good.
Does the construction depend at all at like decomposing and?
You said construction. You said construction.
Oh, there's no construction.
Oh, it's an
Not
existence proof, not a constructive proof,
Okay.
which is the unfortunate part. Yes. Yes. Thank you for pointing that out. Yes. It's so the only known I'll say that the only known constructions that might be outdated. I know that there are constructions that grow exponentially in the dimensions. Okay. And I know that there are approximate ones that do not. Okay, so there are approximate designs that do not scale exponentially. So that's what I can say about that. And here I'm thinking about Emerson has a paper from 10 years ago, which maybe there's something better.
Results on like given group two designs, like other results on how they are related as a group, like. So do they have to be the same in some?
No,
restricted.
No, they do not have to be the same. No, I know that for a fact.
Good.
I know that. I'm just trying to think if there's something more powerful that I can say, and I don't think there is. I know that there are different ones.
I mean, obviously, if you have a K design for K larger than 2, then it will like, and some 2 design, which fails to be a 3 design, then obviously they can't be the same. So, but yeah, I don't know, one has to be a subgroup of the other or something. It would be too easy, I guess.
No, wait, I thought you asked me okay, so I hear 2 questions. First question is.
I asked 2 questions implicitly. So
great. Okay, great. No, they're both good. So I think we sorted out the first one, and the second one is more complicated because now you're going to T bigger than 2. But yeah, I think that's okay.
Slightly naive question, perhaps, but is there any reason that T designs are only defined for groups?
They're not. That's why I said right at the start that oh, you're asking me a more complicated question than that. I thought you were asking me whether a unitary 2 design had to be a group, which is no. Is that you're asking me? Is there a notion of a unitary T design that reproduces the moments of an
algebra?
Yes. Okay, thank you. We need some kind of measure.
But then that's the second question. Is the Haar measure restricted to groups or does it generalize to algebras?
So it's for compact sets, not just groups, it's for compact sets.
So you
So
could
if you
find-
got like a
could find-
compact factor and C-star algebra, then it could work, yeah.
But is that only a finite dimensional C-star algebra, or can it be infinite dimensional?
Well, I don't know the answer to that question. So I know that, yeah, I love your idea. I don't even know if there's been a paper on it, but designs for algebras. And I apologize for first thinking that you're asking a trivial question. So I apologize. You're asking a very non-trivial question. And I do not know the answer, and I don't want to go on record with an answer for infinite dimensions if I don't know. So I don't know.
Fair enough. Thanks, though.
Thank you.
Wonderful. Excellent questions, excellent talk, excellent discussion. That's great. Yeah, it's 4:30. Maybe let's call it a day. It's Friday afternoon. Thanks for listening. Thanks for this absolutely wonderful talk. That was very inspiring.
Thank you.
From the many questions.
Thank you, everyone. Yeah, thank
you. And enjoy the rest of the day, all of you. And the sun in the late afternoon. Thanks for coming. Goodbye. Have a good day.
Bye. Thank you.
Thanks.